Hello. Hello. Hello.
Yes, sir.
Please wait. Sir has not joined. We are waiting few minutes. Yeah. I think we need to call. I think. No? Something. Something. Hello. 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 Hello.
Yes, sir.
Only few students are joining this session. Why? All are requested to rejoin, na? All are requested to rejoin. Only 10 students are joined. So just please inform them. Hello.
Yeah.
Yes,
Am I
sir.
audible?
Yeah.
Okay.
Just proceed, sir.
Is the screen visible?
Yes, sir.
Yes, sir.
I think, in this slide or the next slide.
Next slide, sir. I think.
This one, na?
No, sir.
Okay.
Next one. Next one.
Earlier one. This one.
No, sir. You have discussed this
No,
one.
I have not been in
This one discussed.
this one, na? I have discussed.
Yeah.
Okay. So that is the unbalanced load system actually that also causes imbalance in the system, and that is also a power quality problem. So generally all these are the causes of power quality problem. Next is your power quality evaluation procedure. So how to evaluate if there is a problem that you have detected, then how will you evaluate the problem? So these are the few steps of detection of power quality problems. First is your to identify the problem category. You have to identify that what is the nature of the problem, whether it is voltage regulation or imbalance problem, whether voltage has dropped to a certain value, whether it is a voltage, say it's a flicker or voltage fluctuation, or it is an unbalance. Next is your voltage sags and interruptions, whether it's a short duration voltage variation, which is sag, swell or interruption, or it's a flicker or transients or harmonic distortion. We have to first identify the nature. After identifying the problem nature, then you have to categorize the problem. Categorize the problem on the basis of data, that is the measurements data. You have to measure the data by a power quality monitor. You have to use a power quality monitor for exactly, and say if it is a voltage sag, then how far is the voltage sag is, or if it's a flicker, then what is the flicker intensity. If it's a transient, then what is the peak value of the transient voltage, and what is the rise time, like that. So you have to identify the problem category and the problem severity basically. So severity will be obtained with this problem characterization by the measurement of its actual data. So what are this? They are divided into again three parts. One of the causes of this problem, characteristics, and equipment impacts. So what is the causes? The causes is it's a fault. The fault can be of different types. It can be an SLG fault, or a DLG fault, or a 3LG fault, and even for a SLG fault, wherever the location of the sensitive load also is very important. So how far the feeder reactance is there, as the fault current will travel to that particular location. So that then the impact will be not that high, it will be mild. So the causes of that has to be studied. Characteristics is that how far is the impact, that we have to see, and the equipment impacts finally what is damaged. If that type of problem is caused, whether the equipment trips, or even if it trips, how far it can withstand. So those things needs to be studied. Then is your identify the range of solutions. Now there are, if a problem is found and the solutions are also found, then where will you utilize that solution? Say there are several locations that we can use the particular solution or a mitigation device, whether it should be at the utility transmission system or distribution system, or it should be at the customer interface, that means with the power system and the customer, whether there are an interface, so we have to connect that to the interface, or at the customer system itself, or you need to change the customer design specification. And what is the appropriate solution for that particular problem, you need to study this. Actually means if you go on from the distribution side towards the transmission side and want to deploy your mitigation device, then actually your cost will increase, because your KVR rating will increase. Actually, if you want, say for example, if you want to compensate reactive power for voltage sag, I think you know that reactive power has to be injected if there is a voltage sag, if there is a voltage fall. Then where will you use that? Whether it will be in the transmission, or it is just after the substation transformer at the distribution, or far downline the distribution feeder, where actually. So wherever there will be a change in cost, and there will be a change in rating of your compensating device, where you want to connect that for obtaining that particular solution. That is very important. So identifying the range of solutions, maybe that if you want the same problem can be mitigated if you use a customer device at the at midpoint of a particular feeder, and if you use the mitigation device, say at the starting of the distribution transformer. But if you use a mitigation device at the starting of the transformation of the substation transformer, then the cost will increase. So you have to identify that what is the load area, what is the critical load area, which are basically getting affected with that particular problem. So you can use a low rated mitigation device that will save your cost. So identifying the range of solutions. Next is your evaluate solutions. Now, evaluate solutions means based on modeling and analysis procedures. Depending upon that means say different control strategies will be available for a particular mitigation device. So which control strategy will you adopt, and what are the technical alternatives for that? So all the technical feasibilities you need to study over here. So out of say there are 3 technical feasibilities that you can chalk out, that these are the 3 options that are available for sorting out this particular power quality problem. Then after finding this, then you have to find out of these 3, you have to find the most optimum solution, which is the least cost effective one. This is a cost effective solution, not least. Cost effective means the most cost effective solution. That is the which incurs least cost, least amount of cost is required. So that solution will give you, we have to find this solution. So these are the steps basically. After finding out the problem, you have to find this optimum solution. That is the work basically of a power quality engineer. Yeah. So that also will depend upon what is the location of the sensitive device. It will depend upon the sensitivity of the sensitive device. Will depend upon the nature of the cause of your power quality problem. What is the intensity, and what is the duration of stay in the power system. These are many things, many factors are connected, many factors are associated to find out the appropriate solution for a particular problem that occurs, and with proper measurements also. So these are the 5 steps that we have to do for power quality evaluation for a sensitive device. Next is your broad classifications of power quality problems. Now, under voltage, over voltage, this is what these are the broad classifications. One is under voltage or over voltage. That is actually a long duration voltage variations, which is greater than 1 minute. Voltage sag and dip and voltage swell. This is a short duration voltage variations. Next, voltage interruptions. Voltage interruptions are of 2 types. One is temporary and other one is sustained interruption. Sustained interruption is a long duration voltage variation which is greater than 1 minute. Temporary interruption is a short duration one which is less than 1 minute. So, and next is your voltage fluctuations of flickers. So what are voltage fluctuations and flickers? These are voltage variations which will stay where the voltage magnitude stay within the nominal biasing of, say, if your 1 per unit is your nominal. I think all of you know per unit. Do you know, all of you, what is the per unit measurement of voltage? Hello? Hello?
Hello,
Participants?
hello, dear student, please respond.
Students, do
Yes,
you know
sir.
Please
what
respond.
is per unit? What is per unit measurement of voltage? What is the per unit voltage? How will you find? You know?
Anyone from participant side?
Yes, sir.
Sir is asking some question. Please respond.
Okay. Per unit, I think per unit is being taught actually in this. That is the actual value by base value, na? So you have to find the base value as the maximum value of voltage or current, whatever is per unit you are finding out. So that is the base value, you have to divide by the base value with your actual value to get the Q value. So we are talking about this per unit value over here. So voltage fluctuations and flickers. Fluctuations and flickers are basically these are low frequency variations of voltage. Low frequency means less than the power frequency. So less than 50 Hertz I'm talking about. And its magnitude will not, it will stay within 0.9 pu to 1.1 pu. That is the allowable frequency variation range, 0.9 to 1.1. If the voltage, that is your RMS voltage, This is I am talking about the RMS voltage. Okay. So if the RMS voltage lies between 0.9 to 1.1 pu, it is a voltage fluctuation and voltage flicker. And your frequency of variations should be less than 50 cycles. 50 cycles means that is your 50 cycles per second is your supply frequency. It should be less than the fundamental frequency. And your under voltage and over voltage, these are also all are RMS voltages. So if under voltage and over voltage, if for under voltage the voltage should be less than 0.9. For sag also the voltage should be less than 0.9. For over voltage, the RMS voltage should be more than 1.1 pu. So one lower threshold is 0.9 pu, the upper threshold is 1.1 pu. If the voltage is above 1.1, it is either over voltage for long duration, and for short duration it is a voltage fail. If the voltage falls below 0.9 pu, then either for short duration it is voltage sag, for long duration it is under voltage. And if the voltage stays in between 0.9 pu to 1.1 pu, it is voltage fluctuations and or voltage flickers. And if there is no voltage for short duration, 1 minute, we term that as interruptions. It's a temporary interruption, and if it is greater than 1 minute, it's a sustained interruption. Next problem is your power frequency variations. So frequency variations, as you know that earlier we have that allowable frequency variation range is said to be 49.5 to 50.5 hertz in the interconnected system. As we are all now connected. All the northern, eastern, western, and southern grids are all connected for to have the national grid. We are all in a connected system. Now the grid, the frequency variations are actually not at all tolerable, because wherever frequency variations, how do we get a frequency variation? If there is any mismatch between the supply and generation. Now in this interconnected system, it is very difficult to have that means to have shortfall of power, or if there is a surplus of power at particular end, then that power also can be marketed out to some other areas, to some other loads. So therefore, frequency variations problems is not allowed nowadays in the national grid, locally or throughout the country also. So nowadays, this frequency variation is now, as per Indian Electricity Grid Code, is made much more stiffer. So we'll see that what is the variations. So that is also a power quality problem. Next is your transients, or it is known as surge, that are of two types, impulsive and oscillatory, that we will see. And next is the waveform distortion. Waveform distortion, that is your all our steady state variations. That includes notches, spikes, notches or spikes, same thing. Noise, subharmonics, interharmonics, and harmonics. So we'll in detail we'll see that what are these things. So these are the characteristics of power quality problems. You can see that there are the main categories are divided into subcategories, like say transients is divided into impulsive and oscillatory. Impulsive are further divided into three categories based on their duration. So if the duration is less than nanosecond, it is nanosecond. If it is from 50 nanoseconds to 1 millisecond, it is microsecond. If the duration is greater than 1 millisecond, it is millisecond. And these are their typical spectral content. That means your rise times. So transients, what are transients basically? Transients are actually your voltage variations that will affect only 1/2 of the period of the time period of power frequency. Only 1/2. It will not be reflected to the other half of the cycle. So as the cycle has two halves, power frequency, the power voltage waveform, only one waveform will be 1/2 of the waveform will be affected by a transient. That sort of disturbance is known as transient, not impulsive transient. So impulsive transients will affect only 1/2 of the voltage waveform. But the time of stay is different, and the rise times are also different. Then is your oscillatory. Oscillatory will stay in the system. It is basically oscillatory are more damaging to the system because it stays in the system for longer durations. See, for low frequency, it starts from 0.3 to 50 milliseconds, then 20 microseconds, and high frequency is 5 microseconds. So these are short durations, but these are microseconds means it is greater than nanoseconds. So medium frequency, if it is lesser and lesser duration, its frequency range is greater actually. Clear? So high frequency components are injected into the system. So very high frequency, these high frequency components has a lot of problems, creates a lot of problems as it stays for longer duration. It creates a lot of problem into the system. And if you take the fast Fourier transform of that particular disturbed signal, then you can find out the high frequency components. That is what exactly the high frequency components are present. And the typical voltage magnitude, say, it is 4 times, 0 to 4 pu, 0 to 8 times. You just imagine that, say, if your nominal voltage is 1 pu, and say the nominal voltage is say your 4 or 11 kilovolts, say 11 kilovolt, if I say in the distribution side also, if it is say 3.3 kilo, 6.6 kilovolt. If I say 6.6 kilovolt, then 4 times of that, 8 times of that, you can imagine that how far it will distort. It will affect the power system. And the stay of the, if it is low frequency, then it will stay for a much larger time. Very harmful, these oscillatory transients. Next is your short duration. Short duration variation means from 0.5 cycles to 30 cycles. From 0.5 cycles to 1 minute. That is your short duration. Okay. So short duration includes, again, there are instantaneous, momentary, and temporary. Short duration voltage variations, instantaneous if it is from 0.5 cycles, then half cycle to 30 cycles. And for instantaneous, there are 3 types, categories: interruption, sag, and swell. For interruption, you know that voltage should be very low, less than 0.1 means approximately it is 0. Less than 0.1 pu means it is almost 0. Sag, it is the RMS value between 0.1 to 0.9 pu. If your voltage RMS stays between 0.1 to 0.9, then it is termed as a instantaneous sag. If the duration is not crossing 30 cycles, then we will say that it is an instantaneous sag. Then comes momentary. For momentary, it is duration is from 30 cycles to 3 seconds. That is, magnitude variations are all the same, almost. So momentary, and then it is temporary. Temporary means from 3 seconds to 1 minute. That is the most long duration. Now over here, one thing to say is that sag has 3 types, 3 categories. Now the first category is slow, is very fast. It will be eliminated from the system very fast. Second category, it is the medium one, and the third category, the temporary one, is the long. It stays in the system for longer time. So what will happen is that, say, for a particular sensitive load, if your voltage sag is not that high or voltage swell is not that high, but your stay in the system is very high, approximately the sag or the swell or the interruption stays for 1 minute, then what will the sensitive equipment, say that particular sensitive equipment, if that sag would have been for 30 cycles, it can withstand that. So if the duration for the same sag was small, then that particular sensitive device can withstand. But as now the duration is temporary, or the duration is close to 1 minute, that same sensitive device which can sustain that particular sag for a shorter duration will fail now. So very important over here to find the duration of stay of these voltage disturbances in the system, not only their magnitudes. So both the magnitude as well as the durations are important. So next category, next problems are your long duration voltage variations. Long duration means greater than 1 minute. There also the sag swells will be replaced by under voltage, over voltage, and sustained interruptions, and their respective voltage magnitudes. So for under voltage, as you can see, it will stay between 0.8 to 0.9. Generally, it stays. For over voltage, it is 1.1 to 1.2, not continuously increases beyond that. And next one is voltage imbalance or unbalance. That is also a steady state variation, but the allowable voltage deviation, voltage magnitude variation, is 0.5 to 2% due to unbalance, not beyond that. Current can be unbalanced in an unbalanced situation, but not voltage. So voltage, as it is the common quantity, it is only allowed to vary 2%. That means from its, and how will you measure this? It is generally measured from the average of all the instantaneous magnitudes of the voltage, of the unbalanced voltage, with respect to the average of the balanced voltage expressed as a percentage. Or else for voltage unbalance, we can also measure this from the point of by calculating the negative, that means the phase sequence of that. If you divide the negative phase sequence of voltage with the positive phase sequence voltage and express that as a percentage, then also you will find the amount of voltage unbalance present in the system. So as you know that in case of an unbalanced system, there are three phase sequences that are possible. One is a positive sequence, negative sequence, and zero sequence. Positive sequence and negative sequence have rotating, these phasors rotating in the reverse direction, and these two currents, actually the positive and negative phase sequence, actually flows through the power lines. And for the zero sequence, they are co-phasor, the zero sequence currents. If current can flow, zero sequence current, and they flow through the ground, as they are co-phasor, they are actually ground currents. They flow into the neutral and into the ground. So these zero sequence currents, if they can flow, that means in a YG connection, basically in a transformer, they flows into the ground, and therefore you will not get any zero sequence voltage if the currents can flow. But you will only get a zero sequence voltage if the currents cannot flow. If there is a, say, delta connected winding, or if there is a Y connected winding without any ground. If there is no ground is provided, then obviously currents cannot flow, zero sequence current, and then you will get a zero sequence voltage. So voltage unbalance is very rare to happen, but it is restricted to 2%. Next is your waveform distortions. Waveform distortions has several categories: DC offset, harmonics, interharmonics, and subharmonics is also there. So harmonics is generally, harmonic number is from 0 to 100. That should be without 100, beyond 100 we do not consider, because the magnitude actually falls to very low level. So that does not hamper the device at all. Interharmonics is a band of 0 to 6 kilohertz. All are steady state variations. And interharmonics are what are interharmonics? Interharmonics are basically fractional harmonic number. Say if a harmonic quantity has 1.5 times of the fundamental frequency. If your fundamental frequency is 50 hertz, if you multiply that with 1.5 times, then what will it be? It won't be, say it is, if you multiply with 2, then it will be a second harmonic. If it multiply with 3, it will be a third harmonic. But if you multiply with say 2.5, then it will be an interharmonic, or say 2.25 or 2.15, whatever it is. So any harmonic number which is not integral multiple of the fundamental and it is greater than the fundamental is a interharmonics. Next is your notching. Notching is another problem. It is also a steady state disturbance. It is a continuous disturbance of voltage waveform that is caused by power electronic devices, generally voltage source converters. It is generally caused by the that means the opening and closing of the switches of the converter legs. As you know, say for a full wave converter, fully controlled full wave converter, what if there are 3 legs in a, say in a 2-level converter, there are 3 legs that are possible and 6 switches, then there are instances where these 2 switches gets short circuited, a particular leg gets short circuited with the open, then there will be a voltage disturbance. Voltage suddenly falls whenever there is a short circuit in one leg, and again when the switch opens, other switch opens, then the voltage restores. So that is basically notching. We will come back to that notching, what exactly, when we see the picture. So notching also is basically can be realized by your FFT, fast Fourier transform, if you do FFT. Next is your noise. Noise is a broadband that is your disturbance. Noise is broadband disturbance. Now what is noise? Noise is say unpredictable means high frequency problem, that is your frequency components that are inserted into the system due to the say different reasons, Many reasons are there. Power electronic devices, arcing type of loads, some transients, switching off of capacitors. All these things creates noise, and these are broadbands and cannot be predicted. So this is another waveform distortion. So waveform distortions as DC offset. DC offset. What is DC offset? DC offset is will make the waveform unsymmetrical. Either the waveform will shift towards the positive side, or she will shift down towards the negative side. So DC offset is also problematic, and this is caused by your GMD, your geomagnetic disturbance, and also is caused by rectifier type of loads. So these are the things that we'll discuss later on. So these are the prime deviations of your power quality problems. Next is your voltage fluctuations, which is less than 25 hertz. It should be, I've told that it should be less than 50 hertz, and that is also intermittent. From 0.1 to 7% is your voltage fluctuations. And power frequency variations should be less than 10 seconds. Your duration should be less than 10 seconds, not beyond that. Next, attributes for steady state electromagnetic phenomena. These are the attributes. If you want to measure some steady state electromagnetic phenomenon or steady state power quality problem disturbance, then you have to find its amplitude, frequency, spectrum. Spectrum is a frequency spectrum. Modulation, if it is modulated by amplitude modulation, phase modulation, or frequency modulation, then particular modulation needs to be find out. Then your source impedance, what is the source impedance? And in case of notches, you have to find notch depth and notch area. So we'll come to this. What is notch depth and notch area? So these are the attributes that you have to find for steady state disturbance. And for transient state disturbance, electromagnetic phenomenon, what you have to find? Rate of rise. If rate of rise is very sharp, very small, then the disturbance impact is also that's high. Impact is also high. Amplitude, you want to know. Duration,
hello.
frequency, spectrum.
Excuse me, sir. Hello.
Yeah.
Sir, this session also completed within 5 minutes. So you need to again rejoin on the same link. Okay, sir. Hello.
Okay, after 5 minutes, huh?
Yes, sir. After 5 minutes,
after 5 minutes.
Yes, sir. You have to again rejoin on the same link. Okay, sir. Okay, sir.
Okay. So that is your rate of rise, amplitude, duration, frequency, spectrum, source impedance. Source impedance is what very important. That how much is the source impedance? What we have discussed earlier. That it is the impedance provided by the transformer. If you are finding the disturbance, if you are finding
excuse me, sir. Hello. Hello.
Yeah.
1 minute, sir. Hello, Saurabh Kumar Barnwal. Hello, Saurabh Kumar Barnwal. Mute your device. Saurabh Kumar Barnwal. Okay, sir.
Okay.
You can proceed.
Okay, yeah. So actually, these are the transient state the attributes for transient state disturbances that you need to find. Energy potential is very important for transient state because say for example, a voltage surge, you are experiencing a lightning, and a surge you have experienced a very high voltage that has been impacted by the striking of a lightning. So that what is the energy potential in that surge? The highest, the greater is that potential, the higher will be the impact on the transmission lines or on the distribution lines. So that energy potential is also very high. Higher is the impact means I want to what do I'm hinting at? I'm hinting at the fault level current. So greater is the voltage difference between the that means in that strike that means lightning strike. Higher injected current it will be there in the transmission lines. The fault level current will increase, and the chances of fault and the disastrous fault. Not the fault means what? It is a complete all the three phase faults. It can happen 3LG type, or it can have a DLG type faults. So then the impact, the interruptions will be severe. So source impedance and rate of occurrence. Rate of occurrence is also important. That how fast these things are occurring in case of a transient state phenomenon. How fast or what is the rate. Say if you study for the last 1 week, that in that last 1 week, how many transient voltage disturbances we have observed at that particular load location. That is very important. So these are the attributes that you have to see. Next, we will find in detail. Now we will discuss these power quality problems basically. So first is your voltage transients or voltage surge. What is this? It is an undesirable event that is momentary in occurrence and consists of non-power frequency components. What is that? Non-power frequency components are that it can be some integral multiples of fundamental frequency, or it can be some high frequencies which have no relation with the fundamental frequencies. So non-power frequency components are there in the voltage surge in the that is injected voltage. They are classified into two categories. One is impulsive and oscillatory, what we have earlier seen. So what are the general causes of ferro resonance, faults, transformer energization, and energization of power factor correction capacitor banks? That we have little discussed. What we have not discussed is ferro resonance. What is this ferro resonance? It's basically a non-linear resonance that is observed in transformers, in three-phase transformers. So in some cases it happens that the transformers, three-phase transformers are lightly loaded or not loaded at all, and they are being supplied by large underground cables, UG cables, which have a high capacitance. So what happens is transformer reactance, the line reactance, and the capacitance of the UG lines will interact and will cause a resonance. As you know, for resonance, from your concept, we require both inductors and capacitors in line. Either the inductors and capacitors are in series or in parallel. Both can result in resonance. Both if there is a series resonance or if there is a parallel resonance, in both the cases we see that there will be huge fluctuation, increase in voltage across the storage devices. Storage device over here, what is the storage device? Across the capacitors and as well as across the reactors, across the transformers. So there will be huge that means gain in voltage or it's a gain in current. So that occurs due to magnification. So the same case, same thing happens over here also in case of ferro resonance. But the problem is that for ferro resonance, the transformer core gets saturated. That is why it's the name of ferro resonance. Core gets saturated, the iron part gets saturated, and if iron parts get saturated, what happens is that there are multiple operating points where the voltage and current takes a very high value. Sometimes it is very high, sometimes it is low. Sometimes it is very high, sometimes it is like that. It is a chaotic in nature. The output of voltage and current, if you plot, it will be a chaotic in nature because there are multiple operating points where we get resonance because of non-linearity in the BH curve of your transformer. So that is where it is important that to know what is the ferro resonance. For ferro resonance causes ferro resonance and energization of transformers which draws a very high current, energizing current from the supply, and energization of power factor correction capacitor banks will create